Hello everyone. So in today's video, we're going to continue with where we left off in our last lesson, dealing with how do I optimize, that is, how do I find the maximum or minimum value for a problem, but using a calculus approach. So two of the questions today, we're going to look at just the setup, and then we'll solve one of them in full so we can remember what is the full algorithm that we use to do this. So in our first question, we'll look at just the setup. We have a piece of sheet metal, a flat piece of sheet metal that measures 80 centimeters by 80 centimeters. It's used to make an open top box by cutting identical squares out of each corner. The question here then determine that maximum area. So here is the key. We have this piece of sheet metal, okay, and it's telling us that we are going to cut squares out of each corner so that we can then make a box from that. So the easiest place to start is with a diagram. So we can start to visualize, well, what's happening here? What does this look like? So we have this square piece of sheet metal that measures 80 by 80 centimeters. And then what we're going to do is we're going to cut out each one of these corners, and we're going to cut out identical squares out of each corner. So I'm going to cut that square out of this corner. I'm going to cut that square out of that corner. I'm going to cut the same square out of this corner. And then lastly, I'm going to cut the exact same square out of this corner. If we do that, now what we need to picture is that we could now fold this along these lines right here. So I could fold now right along that line, and that would become the one side. I could fold along that, and that would become the next side. Fold right here, that would become the next side, and then lastly fold right along here, and that would become the last side. So let's try that one again. Okay. So if we fold each of these sides up, then we would be able to create a rectangle. Okay, I'm hoping everybody's visualizing that. That would become a box, pardon me, and that would become the bottom of the box. We would fold that up to become the right side. Fold that up would become the left side. We could fold this and this up to complete the box, and we'd have an open top box as we do that. We're trying to figure out in this question then, how much should I cut out of each corner so that I could then get that maximum volume? Again, we don't know that, so that's where we can start, is that I'm trying to figure out how much do I need to cut out of this on each corner so that when I fold them up, I would get the most amount of volume, or the maximum volume. If you think about this now, as we fold this up, as I define my variable here, the amount that we are cutting out of each corner as we fold that up actually becomes the height of the box. So that's how I'm going to start the question, and I'm going to say, let x represent the height of the box. Now, if you think of our setup from the other day, we would then say, well, first step is to figure out what do we want to minimize or maximize. In this case, we want a maximum, so we need an equation for what do I want to maximize. In this case here, we are trying to maximize the volume. Reminder that a volume for our box will be equal to length times width times height. So as we try to set up this question, then I need to know what is the length, the width, and the height of the box. The height we already know is going to be x, so now I need dimensions for the length and the width. Keep in mind that if we are cutting each of these out, that this side right here will be, say, the length, and this will be the width here. So as we cut the corners out, how much is left for each of those sides? Remember that the full length is 80 centimeters, and we're going to cut off an x, and we're going to cut off an x on this side here. So if I do that, we would be left with 80 minus 2x. In a very similar way, we would end up with the exact same thing here, where this is 80 centimeters, and as I cut off this x and this x on each side, we would end up with the exact same thing. I would have 80 minus 2x there as well. So that means now if we try to create our volume, our three dimensions would be our height dimension, our length dimension, and our width dimension. So there's length times width times height. Slightly different order. All I did is just move the monomial term to the beginning. Now, if we were doing this as we were in our last lesson, we're doing setup only, so I'm not going to do all the work here, but keep in mind that our next step would be then to expand and simplify all of this. And that would give us our equation. Second step, remember that we then would need to figure out, well, what restrictions do I have on this? And that was a new part here that we were looking at. We didn't do this when we optimized questions in grade 10 and 11 with quadratic functions, but with calculus, we do look at what is the restrictions that we would have on our variables. In this case here, restrictions, because we're dealing with a geometric shape, unless it otherwise states, each of our dimensions always has to be greater than or equal to 0. So the amount that we are cutting out of the corner, our height, would have to be greater than or equal to 0. Equal to always sounds a little bit weird, but remember at the extreme case here, I wouldn't really be our optimal solution, but at the extreme case would be to not cut anything out of the corner at all. In other words, x would be exactly 0, and we'd end up with a volume of 0. So what we know is that the height must be greater than or equal to 0, and we know in our optimal situation that's probably going to be greater than 0. We would also have the same type of restriction on our length and our width, which is 80 minus 2x, that's our other dimension, must also be greater than or equal to 0. If we do some quick rearranging here, we would have then 2x is less than or equal to 80, or x is less than or equal to 40. In other words, for our restrictions here, we would have then, if we put these together, that our x value must be less than or equal to 40, and it must be greater than or equal to 0. In other words, our x value is bounded between 0 and 40. So there's our first two steps in the setup. Okay. 1, come up with your variable and what's the equation. 2, figure out what is the restrictions on that variable. And then our third part would be our solution, which we will not complete as we were just doing just the setup here only, but in this case here then we would then be taking our derivative and then we would have v prime at x equals 0 to get our optimal value. Okay, and that's where I will stop in that solution. But that's what that would look like. Again, just trying to help you with the visual. What would this look like if we're cutting the corners out to try to create a box? In the next question, we also are dealing with a box, but we're not starting with a flat piece of sheet metal. Okay, it's simply saying that we have a box, and it gives us a little bit of information here about that box. It tells us that it's a square-based rectangular box. It also tells us that we already have our volume. Okay, if we want to highlight that, we know here that our volume of that box is given. In this case here, though, it's not the volume that we are trying to maximize. Okay, up here we wanted the maximum volume, which tells us what our equation is going to be, what we're trying to calculate. This time what I want to figure out is I want to now minimize, and I want to minimize the cardboard used. Now, if I start thinking about that in terms of a word problem, if I want to minimize the cardboard used, in a word problem or in a math sense, that would be then we are trying to minimize the surface area. Okay, the amount of cardboard would be what is the surface area of that box. And we want to figure out what dimensions will actually do that. Okay, so we got a fixed volume. What's the minimum amount of surface area we can do to get that box created? So first thing I would do here is I would just start with a diagram. So I'd say, okay, visually, what do we have? Okay, do the best you can. I'm going to try to draw some sort of a box here. I'm going to keep this relatively small because I know this solution actually needs a bit of space to be able to get it all in here. So I'm going to say, here's our box. If I want volume, same as above, length times width times height. Important here, though, that this box is square-based. So that means I can say, well, the length and the width are the same. However, the height now is different. So I'm going to start by defining these variables. So I'm going to say, okay, let x represent the length / width. And I'm going to say let h represent the height. And the first step in my problem is that I'm trying to minimize something this time. So I'm going to create my equation. So I'm going to minimize. And I need my equation. So in this case, I'm going to minimize the surface area. So you need to remember that the surface area is just calculating what is the area of all the surfaces. So I have that bottom shape, which would be then x times x, and the top shape, which are identical. So I have the top and the bottom area, which is x squared, but I have two of them. To that, I want to add on the sides. The sides are also rectangular, so the side area would be x times h. However, I have 4 of those. Now, this is the first time that we're actually running into this problem, whether we recognize this or not, is that when we are trying to optimize a function, we need to make sure that the function is written with only one variable. However, here we have x's, but we also have this variable h. So I can't write an equation, or I can't optimize an equation, if I have two different independent variables in that equation. So the first thing I need to do is I actually need to get rid of one of those two variables. Okay, so let's just make note of that. I'm going to say here that you can't have two variables. So to get rid of them, what I'm going to do is I'm going to come over here to the side. I'm going to say, well, what I need is I need some sort of relationship that exists between x and h so that I can get rid of one and keep the other by using substitution. So if I go back to my problem, there was one extra piece of information that we had here, and that was the volume. We knew that the volume in this question was 800 cubic centimeters. If we calculate volume, that means length times width times height. So our volume, x squared times h, must be equal to 800. And if that's true, I can now rearrange for h, and I can say, well, I know that the height is 800 over x squared. And the idea here now is I can take this and I can sub that back in over here to get rid of the h in that equation. So I can say, well, then I know then, therefore, the area, now I'll use our function notation here, saying the area in terms of x is equal to 2x squared plus 4x, and in place of the h, I'm going to put 800 over x squared. I can do a little bit here to simplify. Okay, I can get rid of the x, so I can get rid of one of the x's down here. And then I can rewrite my equation, and often nice to just write this as a collection of terms so that thinking ahead when we go to do our derivative, I can just use my polynomial rule. So I'm going to write this as 4 times 800 is 3200, and instead of writing that as over x in the denominator, I'm going to prep this for the derivative right now and say I'm going to write that as x to the exponent -1. So there is our step 1. Step 1 is we set up that equation. Step 2, again, I know this solution is going to take a little bit of space. Okay, so I'm going to go over to the side here. Say, next part then is I need to look at what are the restrictions on this question. Remember, with any geometric shape, unless there's additional restrictions in the question, the restrictions are always that the dimensions must be greater than or equal to 0. However, if we take a close look here, this one actually says that the dimensions must be at least 8 centimeters. So it's the same idea, except now what I'm going to say is that my dimensions, so one of my dimensions is x, has to be greater than or equal to 8. We also have then the other dimension, which is height, that also must be greater than or equal to 8. However, I don't want restrictions on h. I want restrictions on x because that's the variable that I used for my equation. So now I have to do this substitution over here as well for my restrictions. So if I do that, I will now have then 800 over x squared must be greater than or equal to 8. If we start rearranging here, I would have 8x squared and 800. I would have x squared and 100. And now an interesting step here, I'm going to flip this around because it's easier to see how this works. I'm going to say that we have this. X squared must be less than or equal to 100. Normally, if this was an equal sign, we would just say, well, to get rid of squaring, we do plus or minus the square root. We basically do the same thing here, but it's a little bit interesting what this looks like. If I take the square root of 100, I get 10. That makes sense. If you think of what we're putting here, we're saying the number that it would go in here, x, has to be smaller than or equal to 10. That is true. Okay, I can square any number from 0 up to 10, and that will still stay less than or equal to 100. But normally when we get rid of squaring, we normally would say this is plus or minus. Well, I can't be less than plus or minus 10 here. So this is where we got to be careful. As an inequality, what ends up happening is that negative 10 actually shows up on the other side as a lower bound. And if we think about what's happening here, we're saying that when I square some number, x, it has to be between negative 10 and positive 10 if it is going to be less than 100. If you think about that, that makes sense, okay? That we need to be someplace between these two numbers so that when we square it, we are less than 100. In other words, if I think of numbers on this side here, I could be at, say, negative 1 or negative 2 or negative 3. And when I square those numbers, they would still stay less than 100. But I cannot go beyond negative 10. If I do, say something like negative 11 or negative 12, if I square those numbers, they will no longer be smaller than 100. So the plus minus is there, but it shows up as an upper and a lower bound. Now, remember in the end, our goal is we have to now combine restrictions as we saw in our last lesson. So I now have this restriction here and I have this restriction here. So this is now, if we combine those, saying that we have to be, x has to be greater than 8. X also has to be somewhere between negative 10 and 10. So if we combine those two restrictions together, what we have here then is that if we're got to be greater than 8, that is our lower bound. So x, or 8 is less than or equal to x, and I am not allowed to be bigger than 10. So our number then have to be somewhere. If we combine these two restrictions together, and we must be somewhere between 8 and 10. So there's our upper and our lower bound. The next part then is the actual calculus part, or if we're looking at setting up some headers, I'd say this is our solution. So to get our solution, if I want to figure out a max min using calculus, then we take our derivative. So if I look at our function here, I have a prime at x equals 4x minus 3200 x to the exponent negative 2. We have a prime at x equals 0. If we're trying to find where those horizontal tangents are going to be, that's where our max or our mins are going to occur. That means then in our equation, we would have 4x, and at this point I'm going to get rid of that negative exponent, minus 3200 over x squared equals 0. A couple different ways that we can solve this. Okay, here's one way. We could take the fraction to the other side of the equation. And then we can just cross multiply our equation as we've done with many fraction type equations before. So this then here would give us a 4x cubed equals 3200. We would have x cubed, let's try that again here. We would have x cubed equals 800. And if we take the cube root of both sides, we would end up with x is approximately equal to 9.28. If we check our restriction, we see that this value does fit within our restriction. So now we need to figure out where does the minimum actually occur. So remember our last step here then is to now do some testing. So now we take the answers that we have found from our solution and our endpoints. Remember our max min will either happen at where we have a horizontal tangent. Okay, so here's our horizontal tangent, or the max min may happen at one of the endpoints on our restriction. So I need to test to figure out which one is actually giving us the minimum value. So I need the surface area if we use 8. I need the surface area if we use 9.28. And I need the surface area if we use the upper bound 10. We're now taking these values and we're subbing them back into our original function. You decide which version, but we definitely want to use the one that has the x. Okay, my suggestion would be I would be subbing it right back into this here. Okay, this is calculator work. Okay, so I'm going to go ahead quickly and say, well, I've done the solutions ahead of time. So this one is going to give us an area of 528. This one will give an area approximately 517.1. And this one will give us, oh, sorry, didn't realize I'd written that wrong. Let's do this here. The area at 10 will give us an area of 520. And what we see is that this is the one that's giving us our minimum value. Now, at the very end, we need to go back and reread the question and say, well, what did it actually ask us for? Keep in mind this question said, determine the dimensions that will give the minimum area. So at this point, what we know is that this is happening. So I'm getting this minimum area when the x, remember that's our one dimension here, or our base dimensions. That's happening when x is equal to 9.28. So now we need to sub that back in using this equation right here. We know what the height is. So if I substitute that back in, we can figure out then that the height here is equal to 800 divided by 9.28 squared, or that our height is approximately, well, interesting, ends up being the exact same thing. So we get our optimal volume when the surface area, or the dimensions, pardon me, for the shape are all the same size. So we can say, well, then therefore our conclusion, the dimensions are and we end up with 9.28 centimeters by 9.28 centimeters by 9.28 centimeters. All three sides are the exact same length. Last question that I want to look at is very, very similar to this. The only thing that is different is that I now want to look at a can of corn. Same idea as what we just looked at. Few variations though we're going to add here as well, and that we're dealing with a different shape. We're now dealing with a can, so we're now dealing with a cylinder. It's going to hold 400 milliliters. If you're not familiar with this idea, milliliters as a volume is the exact same thing as a cubic centimeter. Here's one of the differences then. Well, one is that we're dealing with a cylinder instead of a box. The next is that the cost to make this now is slightly different. What we have is that the top and the bottom of the can, they're a little bit thicker, so they cost 10 cents per square centimeter to make. The side is a little bit thinner, so it doesn't cost quite as much. It only costs 6 cents per square centimeter to make. So we're now trying to find the dimensions that will minimize. Here it is. We want to minimize the cost. So there's the equation that we're going to be able to, or that we're going to be trying to find, is we're going to try to calculate what is the minimum cost. And then a few extra restrictions here. We have that the radius must be at least 3 centimeters and the height has to be at least 4 centimeters. Okay, so for whatever purpose, they want to make the can that is aesthetically pleasing, so they have set some restrictions on how big that can be. So again, first place I would start is just a quick diagram so we can see what's going on. So this time we have a cylinder, so I'm going to draw the best cylinder I can. So here it is. Say here's our cylinder. Maybe a quick reminder of some formulas that we have for this. Remember that our volume for a cylinder is the area of the bottom, which is a circle. So pi r squared times the height. For the surface area of this shape, we have a top and a bottom that are a circle. So we have pi r squared is a circle, and I have 2 of them. And we have the side, which if I unwrap is actually just a rectangle. The length of the rectangle will be the circumference of a circle. So 2 pi r is the circumference of a circle times the height of that cylinder. So there is our area or surface area for that shape. So new shape and some formulas here that maybe we got to try to remember way back from grade 9. So as we set this up, we realize that this is based on 2 dimensions. We have the height and we have the radius. So that's where we'll start then our solution. I'll say let r represent the radius and let h represent the height. Next step then, I want to come up with an equation and we are trying to minimize the costs. So I'm going to say we want a minimum or minimize here, and I need an equation for the cost. Now, this is where things get a little bit different again as we set up this equation, because the top and the bottom cost 10 cents to make. So if I want to add that to my equation, I'm going to say, well, my cost, here is the area of the top and the bottom, and we now need to incorporate the fact that they are going to cost 10 cents. So in our equation, this shows up by saying it's 10 cents for, actually let's put that in a different color. It's going to be 10 cents for the top and the bottom, and we have to multiply it by the area. So the top and the bottom, 2 pi r squared. To that, we would need to add on the cost of the sides. The sides are going to be 6 cents per square centimeter. So in our equation, that will show up then as 6, and we need to multiply by the area of the side. So there it is. So that's going to show up here now in our equation. Or if we simplify this, our cost then is 20 pi r squared plus 12 pi rh. We run into the same problem that we did in our last question, and that is that we have 2 different variables. We have an r and we also have an h in this equation. So, like we did in our last one, we go to the side. We say, well, can I create a relationship between these 2 so that I can get rid of, through substitution, one of those 2 variables? Like our last one, again, what we know is this volume. So I'm going to create an equation for that volume, which is then we have that pi r squared h must equal 400, the volume. Again, you're allowed to isolate for whichever variable you want, but if I take a look at this equation, we have more r's than h's, which is one clue. I only have this one h. If I take a look at this equation, it's also going to be easier to isolate for the linear variable h as opposed to this squared variable r squared. So I'm going to isolate for h here. So h is 400 over pi r squared. So if I substitute that into the equation, we actually now have that the cost in terms of the radius, so we'll have only one variable now, is 20 pi r squared plus 12 pi r, and in place of that h, I'm going to put 400 over pi r. Sorry, pi r squared. Missed that squared the first time. We can do a little bit of simplifying like we did in our last equation. We do have to be careful though. The pi will divide out the pi, and we have one r, and down here we have two r's. So as I divide those out, we're going to now be left with our equation. 20 pi r squared plus 4,800, and like we did with the last equation, I'm going to take the r out of the denominator and I'm going to use a negative exponent. I'm just thinking ahead a little bit about taking that derivative. So there's the equation that we're going to need to minimize afterwards. Our next step is our restrictions. So if I think of my restrictions here, again, our restrictions are always that dimensions must be greater than or equal to 0 unless there's some additional constraint. And notice that we have two of them here. The radius has to be at least 3 centimeters. So that's where I'm going to start. That the radius has to be greater than or equal to 3. And then we have that the height, different restriction. In this case, the height must be at least 4 centimeters. So I'm going to say here then our second restriction is height is greater than or equal to 4 centimeters. We want our restrictions though for this equation to be based on r. So as we do that down here, then we need to get rid of the h. So similar to what we did in our previous question, I'm going to use that substitution here as well. So I'm going to say that we have 400 over pi r squared must be greater than or equal to 4. Again, rearranging similar to a linear equation or a quadratic equation, I'm going to multiply that fraction out so that I have 4 pi r squared. I'm going to divide out the 4 pi. Notice that the 4 will divide out nicely so that I get 100, but the pi does not. So I'm going to leave it as an exact answer. Again, as we get rid of square in an inequality, I like to have the variable on the left-hand side because that kind of sets up my last line. And that's when you get rid of the square, the answer is plus or minus, but the plus goes on one side and the minus goes on the other. It actually creates an upper and a lower bound. So as I get rid of the square and I take the square root, again for our problem I'm going to use a decimal answer. So I'm going to say the upper bound, if I do the square root of 100 over pi, is 5.6. Keep in mind though, I get that plus minus idea. In an inequality, the negative answer shows up as the lower bound. We need to combine these restrictions together. So I have this restriction and now I have this restriction. So overall then, if I want my upper and my lower bound, the smallest this can be, well, this is saying this has to be greater than 3. This is saying it has to be greater than negative 5.6. So we always have to pick the more restrictive value. So that means then the more restrictive value is that we have to be bigger than 3. So that's my lower bound. And my upper bound here then, the only one that I have is this here, that r has to be smaller than or equal to 5.6. So there's my upper bound. So there's our restriction. And then that's where I'm going to stop because this question said just to look at the setup only. If you want to finish the solution, you can, but that would then be my next part is I would need to do what is the solution. So this is where now we would take our derivative of the area. Sorry, not area, the derivative of the cost in terms of the radius. Okay, we get our derivative, and then we would do c prime at r equals 0 for horizontal tangents. And then lastly, we would need to then test any values that we found. C at, and we already know we would need to do C at 3, C at whatever values we get from this part here, whether that's 1 or 2 or 3, however many values we get, and then I would need to do C at the upper bound as well. So what is the cost at all of these values to figure out which one is actually giving us the minimum cost. Okay, so there's our setup without doing a full solution. So a few things in this question that are a little bit different. One, that we're dealing with a cylinder. Two, we have added in a cost component, so it's not just a surface area question, there's a little bit more to it. And again, we're dealing with formulas that are a little bit more complex, having to deal with pi and how that all works through. There's some practice questions. I have provided full solutions, so take a look, see what you can do, and we'll continue looking at more max-min questions, optimization problems tomorrow. Have a good day, everyone.